Good morning. So this talk is going to be about my experiences in deploying differential privacy in practice and some of my learnings, both from a theory perspective and from an engineering perspective while designing the system at scale. One thing I want to put out as a disclaimer, whatever I'm going to talk in this talk is primarily based on scientific principles and publicly available information. It may or may not corroborate to any particular deployment by any organization. So with that disclaimer, let me start. So as I told you, this talk is going to be about deploying differential privacy technology in practice. Now, what it really means, a privacy technology, you need to have a problem to deploy it. So the first part, what I will do is I will set up the specific problem we want to look at and motivate why the requirement of privacy is a very natural thing to have. And then I would try to motivate why differential privacy is probably one of the most natural choices to make for this particular problem. Hence, we start with learning from private data. So the first problem we would look at is learning new words. So there are a lot of devices people use, and people write a lot of stuff on their keyboard. These are extremely sensitive information, like talking to their doctors, talking to their friends on WhatsApp, or to their family. And at a data server, a data provider, like let's say Google, Apple, or Microsoft, I would want to know what are the new words people are typing. And why do you want to know that? Maybe to understand a particular trend, probably during election, what are the words people are typing. And also provide better predictive keyboard. And I'm emphasizing on the term new word because I'm just not trying to find out the frequency of a word, I'm actually trying to discover that word. And even in today's world, this is not totally true with English because we have publicly available data, but for other languages like Mandarin and some of the Indian languages, we really don't have enough information about what are the new things people are typing. And certain interesting things also come into the picture. For example, there are certain words which are used in one version of one language is not used in the other version. For example, in Indian English, a lot of times we use the word prepone, which is basically the opposite of postpone. Well, that does not exist in US or British English. So these are the kind of words you might want to learn. Sometimes some form of expression, let's say aw. A lot of people write AWW, a lot of people write AWWW and continues for like 6-7 characters. So these are the things we want to learn. So this is one of the problems we would look at from the perspective of privacy. And clearly, privacy is almost self-motivated here because really you don't want people to know what you are typing. Another example is learning the frequent URLs people are visiting. The motivation is that you want to learn about these things. This might be useful for figuring out what the malicious URL people are visiting to. For example, what are the malicious URLs people have set as their homepage. Or it also might want to allow you to figure out typo squatting. For example, if you want to go to Air France, instead of that by typo you go to Air France. This might be a malicious website, and if a lot of people are going there, then you know that the frequency of this URL would pop up at a server side and you can do something about it. The third example, this is not probably as dire or as serious, but still, you might want to figure out what are the frequent emojis people are typing on their keyboard. Well, you want to reorder the emoji keyboard maybe to allow people to kind of figure out the frequent emojis people are typing, and you can just go and type that emoji. For example, I think last year the poop emoji became really famous. And also this gun emoji, I think, had something like initially there was a real gun that was put as an emoji, then the company actually changed it to this toy gun. So in any case, you want to learn these things. And privacy is a serious concern because you want to ensure that whatever statistic you are learning at the server should protect the privacy of the individuals who are participating. So there are some other applications of the same technology or the tool I will be telling in this talk, but I will not get into the details of it. For example, it can be used for health data. You might want to get some health information about your population, and today smartwatches can collect a lot of health information about people. So this is for the well-being of the user base which the company has. It may be also used for learning about device telemetry. For example, you might want to know how much battery a particular app is draining. So you might actually force it to do something else. And the final thing is actually launch a full-scale predictive learning system at a distributed setting. So you want to learn a particular model based on the user's data. And these are completely distributed. So these are the things I'm not going to get into. The things which I'm going to talk about are the simple problems of learning this frequency statistic or actually learning new words. Well, when I say the word simple, it might seem like, why am I solving a simple problem and why am I wasting 45 minutes of your time? Because differential privacy has been there for like 10 years. What I realized while developing this project, in the first 1.5 months, I actually thought it to be, my knee-jerk reaction was, it's a simple problem, I will take up a paper, implement it, done. But what it turned out is, when you start thinking of this problem at scale and actually deploying it, there are certain challenges you face, and it forces you to actually design new theory also around it. So that's the thing which I'm going to kind of motivate in this talk. So let me kind of set up the problem in a more formal setting. There is a server, and there are a bunch of devices which are communicating to the server. And the server is collecting statistics from each of these devices and produces finally useful information. This might be the new words which are frequently typed by the user base, or it might be a complete histogram of the emojis people are typing. So these are the kind of statistics which I'm expecting the server to produce. Now, from the context of privacy, let's try to see where the trust boundary lies. So there are these devices which send statistics to the server, and the server produces an output which is useful. There might be an attacker who might actually sit and look at the output produced by the server and try to infer specific information about an individual. So that's the first type of attack I want to protect. Even worse, there might be an attacker at the server itself and actually look at the stream of information given by the devices and try to figure out specific information about an individual. Now we want to protect against this sort of attack also. So in a sense, my trust boundary is just the device itself. And when I say the trust boundary is just the device itself, we might say that like Google owns Android and Apple owns iOS. What does it mean to have the trust boundary? Why am I not trusting the organization of the server? Well, the code that is running on your phone, you can actually decompile and see the code. So in that sense, you don't need to trust the organization. And in principle, at the very least, like if you know how to decompile, in principle, at the very least, you can verify what it is doing, what it is promising to do. So in that sense, the trust boundary is the device itself. Now, this setup is not new. So this setup has been studied for the last 5-6 years in the context of data privacy and in particular differential privacy. And what we have seen is that there are two conflicting trade-offs, utility and privacy. You want to protect privacy because that's the first goal, to kind of protect your user base. But at the same time, you don't want to be protecting privacy to the extent that the output becomes meaningless. So you want to have some utility of it. In the other side, you don't want to be so much accurate that actually you give up on privacy of individuals. And it turns out that balancing this trade-off is a really hard problem. And over the past 10-12 years, we have seen a series of attacks, and these are like real industrial attacks, which have kind of time and again told us that we should look at a rigorous and a formal notion of privacy. So it is absolutely important to define what it means to be private, rather than coming up with a mechanism which says that, okay, this mechanism satisfies privacy. But it's very important to define what privacy means. So in this talk, along with talking about the utility privacy trade-off, I will bring into another component which I believe is equally or more important as the utility privacy trade-off. Because when you build a system, it has to produce reasonable output in reasonable amount of time under the reasonable constraints of the setup. So the other constraint we want to kind of play a trade-off with is the computation and the communication. So how much computation the client is doing, how much computation the server is doing, and how much amount of data that is transmitted from the client to the server. And balancing this trade-off is as important as balancing the utility privacy trade-off. So the notion of privacy we'll be using in this talk is local differential privacy. This definition has been kind of reinvented over the years. The first version was in this paper by Warner in 1965. It was a statistics paper. Then it was reinvented by Efimescu et al. In 2003. And the modern definition, which I will be working with in this talk, is by Dwork, McSherry, Nissim, and Smith from 2006, which got them Gödel Prize this year. So the idea is the following. Suppose your device has a data sample, and there is an algorithm which is running on this data sample and producing the output to the server. Now, for the context of the talk, assume that this algorithm is randomized. So it has access to random coins. Now consider an alternate scenario where the data sample is changed to something arbitrarily different from the original data sample. And the same algorithm is running on the data sample and producing the output to the server. The requirement from the perspective of privacy is that A of D, this is output on the data sample D, the actual user's data sample, versus A of D prime, that is on data sample which is arbitrarily constructed. These two outputs should be close in distribution. Now why can I say closeness in distribution? Because A is a randomized algorithm, so A of D is a random variable. So what I'm wanting is A of D and A of D prime should be close in distribution. Now it is not important for this talk what it exactly means to be close in distribution, but there is a formal way we can define the closeness in distribution. Instead of giving the formal definition, let me tell you some of the semantics of this definition. The first thing is there is this parameter called epsilon. So this is what you can call the privacy knob. Smaller the value of epsilon, stronger privacy you have. Higher the value of epsilon, weaker privacy you have. And this epsilon, in a sense, what it is controlling is, when I say this closeness in distribution, how close this A of D and A of D prime are. One of the reasons why differential privacy has been attractive, both in the academic and in the industrial setting, is the semantics of the definition is meaningful even in the presence of arbitrary auxiliary information. So it really does not assume anything what the adversary knows. The semantics of the definition still holds meaningful. And this is important if you are trying to build a large-scale system, because you really don't know who your adversary is. The third thing is that differential privacy formally protects you against membership attacks, meaning that if you run a survey, let's say on a bunch of users, and produce the output, it is not possible for an attacker to look at the output and decide whether a particular user or a person was there a part of the data set or not. The membership cannot be decided. So it protects you against membership attacks. And hence, we like this definition of local differential privacy in the context of the problem. So differential privacy is the notion of privacy we are looking at, and the word local comes from the fact that my trust boundary is just the device itself. So anything that goes out of the device should be differentially private. So there have been some deployments on similar ideas. I can't say how similar they are. And these are a couple of my patents from Apple. These are granted patents which are on similar ideas. And there is a project from Google, the Rapport project by Erlingson et al. From 2014, which is used in Chrome today. So these are the three at least ones which I know of. Please pardon me if I don't know of other ones. So this is the premise with which I wanted to start the talk. So till now I've told you what it means to learn from private data. What are you going to learn? And now, in the next part of the talk, I will primarily focus on this problem of learning new words with privacy. What are the challenges that come up? And how those challenges actually drive you towards designing a quote-unquote optimal algorithm. And finally, I will talk about some of the engineering challenges which one faces while deploying the system. And when I say engineering challenges, I will not say some of the solutions. There are a few of them which I know the solutions to, and few of them are open questions to think about. So let's come to the next part of the talk, which is learning new words with privacy. Just to remind you, what is learning new words? You have these devices, people are typing words, and you want to find out the words which are typed frequently by the users. So to solve the problem, let's actually formalize the problem. So the formalization is called private heavy hitters. So this problem has been studied from 2012 by Su et al., then the paper by Erlingson et al. In 2014, and a recent paper of mine, which is under submission, with Basili, Stemmer, and Nissim. So the problem is the following. You have a bunch of data samples, D1 till Dn, from some really large domain. So it is physically not possible to actually scan through the complete domain. So this domain is S, calligraphic S. And each of these devices sent differentially private information to the server. And the objective of the server is to produce what I call the gamma heavy hitters. So the heavy hitters are the elements in the domain whose frequency is at least higher than gamma. So gamma, let's think of it as a parameter. So we want the gamma heavy hitters. Along with the heavy hitters, we actually want to know their frequencies. Want to know the frequencies of the heavy hitters along with this parameter gamma. Now, intentionally, I did not actually write the exact value of gamma which we can achieve, but we will see that there is a constraint which is placed by differential privacy in itself to what gamma can be. Because differential privacy does not, differential privacy protects you against membership attacks. It basically also means that gamma cannot be 1. Basically, users are protected, participation of a user is protected, so you cannot figure out elements whose frequency is 1. So there is a lower bound through which we can go, and in the course of the talk I will tell you what gamma we can achieve and why that is the best you can achieve under privacy. So that was the privacy utility part of the problem, and as I told you, there are computational communication constraints which one has to deal with. So from the client side, you want your algorithm to run efficiently in the size of the domain and the number of samples. Now, I told you the size of the domain is really large. Even the number of samples is really large. Just think about the number of cell phones people have in this planet. It's more than 300 million. The communication to the server from the client has to be efficient. It should send very few number of bits. Well, because first of all, communication is expensive, it is time consuming, and also it is using people's data bandwidth. And similarly, the server-side computation is also an important concern because you want to produce these outputs at a reasonable time. In particular, if you want to catch a trend during election, it is no use to produce the output after 1 month. Now, these are the constraints we are working with. So notice that I used English phrases like efficiently, very few bits. So these are not like specifications, right? In the next few slides, I will tell, given the setup of the problem, you can actually formalize what it means to be efficient, what is few number of bits, how much computation you can tolerate and how much communication you can tolerate. So that will be given by the problem specification itself. And this will also highlight why there was a need to design a new algorithm. So let's look at the client side. So we said like it should run efficiently in the size of the domain and the number of samples. Consider Chinese simplified. So this, I have to put a disclaimer, I don't read Mandarin or Cantonese, so my knowledge is from Wikipedia for this. So please pardon me if I'm making a mistake. So the number of characters is more than 3,000, and let's say I'm trying to learn 8 character words. So the total size of the domain is 3,000 to the power of 8. It is formidable. And your number of samples is 300 million or even higher. Now, the previous work by Basili and Smith 2015, they gave an algorithm where they meant efficiency to be polynomial in n. So it is n to the power of 3 by 2. Now if you plug in these numbers, it is almost impossible for a cell phone to compute, and even if it computes, it will drain out your battery. Doesn't work. So in this work, what we mean by efficiently is it should run logarithmic in the size of the domain. That is achievable. So now I have defined what it means to be efficient from the perspective of the client. Now in terms of communication, we said like very few number of bits. So this actually the previous paper got it right. So it is constant number of bits. In fact, you can show that you can get it down to pretty much like 1 bit, which is kind of surprising. The server-side computation, similarly, the work of Basile and Smith. By the way, I'm referring to Basile and Smith because this was the best known before we started the project. So the work of Basile and Smith, the server-side computation was 10 to the power of 5 by 2. If you actually plug in the numbers, it goes into days of processing. Here, the efficiently what we mean is it should run linear in the number of samples and logarithmic in the size of the domain. This is actually achievable in reasonable computation time. So this is the setup of the problem we are looking at. So we are looking at finding out the new words which can be formalized to private heavy hitters. And for heavy hitters, we have some computational and communication constraints which have primarily been brought into from the perspective of the scale of the problem. Now, learning these new words is a hard problem. Like you want to find out something which you have not even seen. Furthermore, you have a channel which is sending you extremely noisy information. So we'll try to solve a simpler problem first and then show that we can use that simple problem as a black box to solve the actual problem of finding out the heavy hitters. So the problem we are trying to solve right now is finding out frequency of a bunch of words or terms under the constraint of privacy. So this is a short interlude. The algorithms in this section would be based on my submitted paper, which is also there on archive, and the patents. So what is the problem of private frequency oracle? Here, the only difference is that you have access to the dictionary. So you know what you are searching for. You are just trying to figure out the frequency of the words which you are searching for. So you want to find out a histogram over the words, and you want to ensure that your estimation of the frequency for each of these words collectively has low error. And when I say low error, here the error is in the order of square root of n log of the domain size. And notice that there is a theta here, which basically means under the constraint of privacy, you cannot achieve better error than this. So this is the tight bound in the error. And remember in the frequent heavy hitter part, I did not define gamma to be. Like what was gamma? Now this defines what my gamma I can achieve. Because if I cannot solve the frequency problem with error better than this, then I cannot solve my heavy hitter problem too. So we'll try to find out new words essentially whose frequency is at least square root of n log s. Yeah, sure.
So is the dictionary size and the size of the domain the same?
Yes. Okay. So let's try a starter solution. This is a very simple solution. This will achieve the actual optimal error guarantee. But clearly I have few more slides, so that means that will be not the one which you are hoping for. But anyways, so let's start it. It is a very good building block. So the algorithm is very simple. Take the data sample and map it to a vector of the size of the domain. Of the size of the domain S. So basically, if the data sample is the ith element in the domain, just go and put a 1 there and 0 everywhere else. So this I will call to be the one hot notation. So it's 1 and 0 everywhere else. Now, to ensure differential privacy, you flip each of these bits independently with some bias, and that is your randomized response. It's a vector which has been randomized by flipping the bits. And what one can show is that if the bias of these flips are properly calibrated, then this would satisfy epsilon differential privacy. It's not important for the talk what that bias exactly should be, but it can be calibrated to satisfy epsilon differential privacy. Now the algorithm is actually very simple. So each of the devices sends this vector of flipped bits. The server just adds up these bits. And essentially, this gives you the histogram. Well, this is a noisy histogram because you have flipped the bits. But this gives you the histogram, basically meaning that if you want to figure out the frequency of the ith element, you just go to the ith column of the summed up vector, and whatever value is that is the estimated frequency. Surprisingly, this algorithm actually achieves the optimal error. So this very simple algorithm gives you the optimal error guarantee. So in some sense, it actually balances the utility privacy trade-off. But the problem is the computation and the communication. So let's see what is the computation and the communication. The client-side computation is order S of the domain because you have to flip each of the bits independently. And once you flip the bits, the vector which you get is a reasonably dense vector of zeros and ones. So you have to send order S bits to the server. Furthermore, the server-side computation is also in the order of S. So your computation both on the client and the server side is formidable, and also the transmission. So this can work for very small domain, but the scale of problem we are looking at, there is no hope of using it. So now let's try to reduce each of these parts one by one. The client-side communication, the client-side computation, the communication, and the server-side computation. So looking at the client side. So we are trying to reduce the client-side computation. So the idea is we'll use a tool from data streaming or sketching called count min sketch. First I will give the idea without privacy, then I will show that it is almost immediate how to make them differentially private. So what's the idea? You take the data sample and hash it with k different hash functions. For technical reasons, these hash functions have to be pairwise independent. So you hash the data sample into k different hash functions, and each hash function maps the data sample to a range of square root of n. So notice that initially I had this ginormous vector of length s, I've got it down to root n. So each hash function maps the data sample to square root of n bits. And when I say maps it, basically it takes the hash of the data sample, whatever the value between 0 and square root of n, it just puts 1 there and 0 everywhere else, and it does it for k copies. Now what I've done this is I've traded off this long vector with a bunch of these short vectors, and have kind of distributed this one single bit of information across k bits. So now what is the computation? Well, if k is the number of hash functions, then it's order log s. Well, I'm kind of putting log n terms under the rug because log n is really small in this case. But it is log s because you need like log s hash functions, and you have to kind of take the hash of the bits.
One more question.
Yeah, sure.
So is your construction black box in some sense? If I give you any other count min sketch algorithm, you can use it?
No, it is not black box construction.
It's not relativized.
It's not relativized. So you take this. Now, what you do is you take this like just a moment. So you can see that this is a matrix now, right? It's a matrix of k cross root n. So each device kind of sends k times root n bits to the server. The server basically does the same thing again. It just adds up these matrices. Once it adds up the matrices, it gets a matrix of bunch of numbers. The size of the matrix is k times root n. And now comes the interesting part. To estimate the frequency of a particular term, what the server does, it takes the hash of this term, k hashes, and goes to the corresponding bins, denoted in this yellow, take their value, take the mean of them. And hence the term count mean sketch. And that is the estimated frequency. There is a very simple intuition why this actually gives you something interesting, but I will not get into the details. So the error in this estimation is square root of n log s. So this is non-private, but what I have shown is that you can have a construction with much fewer number of bits and have an error which is at the same order of the private algorithm which I could actually hope for. So asymptotically I should not be changing things if I'm using the same algorithm. And the server-side computation is square root of n log s. Now it turns out how to make this algorithm differentially private. So the way to make this algorithm differentially private is, well, flip each of these vectors, bits in these vectors, because each small vector is one of those, like the ginormous bit vector I created for the randomized response in the original solution. We just flip each of the bits. But this is k epsilon differentially private because in essence you have like k copies of information which you are sending. So the privacy guarantees kind of add up and you get k epsilon differential privacy. But this doesn't solve two problems. First, it kind of increases your privacy requirement from epsilon to k epsilon. And second, you are still sending quite a few number of bits. So now the trick you do is you sample one of these hash functions and then randomize the bits. Once you do that, what you can show is sampling ensures epsilon differential privacy without hurting accuracy. In fact, it actually improves the accuracy by a square root of k factor. So this was a new insight we got through our project, and this is a theorem. But still we have like root n number of bits to send, and if n is 300 million, it's not still achievable. It's like quite a few number of bits. Here comes my analogy with bread and jam. The problem is that there is one single bit and a lot of zeros. So consider this hypothetical scenario. Suppose I give you a piece of bread and either I put a drop of jam or I don't, and I tie your eyes and I ask you, did I put a drop of jam or not? You have to really touch at every point in the bread to figure out whether there is jam or not. But what a smart person would do, he or she would take a bread knife and spread this jam all along and touch one of the places. If I find the jam to be there, then the bread has jam or it doesn't. So the trick is actually to spread the information across all the bits. And the tool that we use is called Hadamard transform. This is from physics, like in 1800s. It's quite common used in quantum mechanics, but in this case it's very useful for us. And this is without loss of information. So it's a basis rotation which basically spreads the information all along. And going from this sparse representation, you go to a very dense representation where every bit has some information. Now, you sample one of those bits, flip it, send it to the server. The combination comes down to one bit. Well, you need log n bits to kind of tell which bit you are sending. But the theorem is that this sampling and this Hadamard transform does not hurt accuracy. So, in essence, we have achieved the optimal error with the effective client computation of order 1 bit now in this case, because I'm sampling just one of the hash functions and sending. The communication to the server is 1 bit, and the server-side computation is square root of n log s. And the error is still root n log s. In the interest of time, I will skip the experimental section, but this slide is primarily to show that whatever I'm saying is not useless and actually works in practice. But if you are interested, please talk to me after the talk. Okay, so now we have designed an algorithm to estimate the frequencies. Now let's get back to the original problem of solving the heavy hitter. So remember, I want to find out all terms whose frequency is at least higher than this square root of n, right? And we have these constraints on the client-side computation, the server-side computation, and the communication. We don't want to compromise on that. Now, to solve this problem, any element in this domain S can be represented as a bit vector in log S bits. right? I'm not going to scan through the complete domain, but I can represent this in log s bits. What I will do is, the idea is to construct this heavy hitter bit by bit. The term bit is used here kind of in a generic sense, because if you are dealing with languages, you might not want to do with bit, but you want to do with alphabet by alphabet or character by character. But for theoretical purposes, talking about bit by bit is useful. So you want to construct this, the heavy hitters bit by bit. And the main idea, is that you want to construct it bit by bit. So you start, when you are thrown with a problem in computer science, pretty much the first knee-jerk reaction is to start with a tree. We'll use a tree. So start with the null set. Then first figure out whether the bit 0 is sufficiently frequent or the bit 1 is sufficiently frequent in the first location. So one thing to notice is that if a term is frequent, its subsets are also frequent. So this is the first observation. And I can use to figure out the frequencies of the subsets by my frequency oracle. Remember that I designed a differentially private frequency oracle. Yeah, if a string S is a heavy hitter, its prefixes are also heavy hitters. Now what I do is I figure out which of this bit is frequent, and I go down one level in the tree to the second bit. Now the question is, by doing this, the span of the tree is increasing, right? At every level, it doubles. So if I open up too many nodes, then my computation goes off. Now the idea is that there can be at most root n such nodes in every level, because the frequency of each term is at most root n. We are looking at like heavy hitters of size root n, and there are n data samples, so there can be at most root n number of nodes in the at each level which I need to open up, and that's pretty much the algorithm. So this algorithm actually gives you square root of n log s error, runs efficiently in time log s. The client still sets order 1 bits, and the computation of the server is n log s. So this is actually achievable. If you plug in the numbers, this is an achievable number in practice. Well, I use big O notation, but trust me, the constants are not horrendous. Okay. Again, in the interest of time, I will skip this slide, but if you actually use it in practice, when I say use it in practice, I can't give confidential numbers, but this is from the paper we wrote and something which I ran on my laptop with 10 million samples. This runs with 10 million samples with like really large dictionary on my laptop, so it does not require like server class computation. You can achieve reasonable error. So again, I will talk about this after the talk if someone is interested. So that brings me to the last part of the talk, which is some of the engineering challenges I faced. So in this 3 parts, I told you like how it kind of forced us to design better algorithms, like how the scale of the problem actually forced us to design a better algorithm. Now in this part, I will talk about some of the engineering challenges I faced, and they were kind of unique when I actually started solving the problem, and I don't even have answers to all of them. So some of the challenges. First, theory bounds, the big O bounds are loose in practice. In reality, you really want the actual error we are getting in estimation. In research papers, we can write that very easily because I really have the data. When I'm deploying these things in practice, I don't have the real data. So how do I say how my algorithm is performing in real life? And this is a very natural question we get. It's like, okay, I have invested so much of money in your project. Tell me what you are getting and how much you are missing out. What are the words you are not capturing? So, but you don't have the actual words. That's the whole point of solving this problem. So here you can use an intuition, and this is not theory. This is like I will call hack or empirical process, which kind of worked out in practice. The error in frequency of estimation is independent of the true frequency. The noise you introduce because of differential privacy is independent of the true frequency. So once you make this, once you kind of have this in your mind, immediately you have a solution, because there is one term whose true frequency you know, and that term is the one that is not there in the data. Its true frequency is 0. So if you hit that term on the sketch object, you are just going to get pure noise, and that will give you the band of the noise you are supposed to get in the experiment. This actually worked. Some of the other challenges are how to design a test pipeline for this kind of systems. Basically, if you design the systems, it's important to test that. The quality of randomness is very important for this kind of systems. I really don't know what's the right test pipeline to design. So it's a question kind of to be answered. And the last one is more of a philosophical question. Like, what is the choice of this parameter epsilon? I mean, even now I don't understand what's the right value of epsilon people should use in practice. And there are like so many companies using differential privacy today. So it's kind of a request. And this idea, I should attribute it to Cynthia's work, is that once you are deploying these systems, you should publish the actual value of epsilon you are actually using in production. So this at least allows people to actually scrutinize that. And also actually publish the algorithm which you're implementing. So to end, I told you about how to learn from private data, what are the algorithmic challenges we faced and how we designed a new algorithm. And finally, I told you about some of the engineering challenges I faced with few answers to them, and most of them are questions. Finally, if you have not heard the complete talk, just remembering this slide is good enough. There is utility privacy trade-off. And at the same time, when you try to implement the systems, there is a trade-off of computation and communication. And that's pretty much the talk.